30 now. So we'll move on to our next contributed talk. I should have asked you before, Thomas, how do I pronounce your surname?
Lesgourgues.
Lesgourgues. So we'll have Thomas Lesgourgues speaking to us about minimum degree of Ramsey-minimal graphs. Floor is yours, Thomas.
Yeah, thanks, George. Yeah, I was saying I'm going to cut my camera because I need to write on the laptop. Otherwise, we're just going to see my setting. So thanks for having me. I'm one of the organizers, so I guess thanks me for having me. And I'm just putting everything on the screen. So today I want to talk to you about a topic on Ramsey graph. And it's not my most recent result, but it's a result I like to explain usually, and I like to talk about because, especially at conference, because it's a joint work with Anurag Bishnoi and John Bamberg. John is from University of Western Australia, and Anurag is in Delft now. And it's a problem where you look at the full proof, we actually use probabilities, we use finite geometry, we have a bit of group theory, we have a bit of irreducible conics on finite fields. And it's typically the kind of work you can only do if you talk to different people. So I think it's a good example of why people should talk at conferences. So a bit of setup initially. I'm going to repeat some stuff that has been said already, so I might go a bit fast, but my topic is on Ramsey theory. And let's say that we start the problem with a number or color, R, and a complete graph, KK. So just to be clear from the start, what I mean by a complete graph, KK, is a graph on K vertices where you have all possible edges. So the triangle is K3, and then you can have, for instance, K5. It's going to be like this star with all the edges. So if you have a problem when you start with R colors and graph KK, we said that the graph G is Ramsey for KK. If for anywhere you try to color the edges of G, you end up with inside a monochromatic copy of KK. So to have an easy example, and to go back to the example that Sam talked about on Monday, the very famous example is that if you start with K6, so 6 vertices, a complete graph from 6 vertices, and you try to colorate that with 2 colors, then whatever you do, you will have a monochromatic triangle in there. So what does that mean? It just means that K6 is Ramsey, and that's the notation we use in 2 colors for K3. Okay, so for whatever way I color the edges of K6 with 2 colors, I end up with K3. And so that's the first basic definition. And Ramsey graph is a very active field of research in combinatorics. And what we want to understand quite usually is we want to understand the graph G. What are the graph G? What are their properties? So that why do they become Ramsey for KK? The very first one, very famous one, is the one that Sam talked about, the Ramsey number. And I think he wrote it like that. So the R color for the clique size K. And he showed that we know asymptotics, but we know actually not that many things about that coefficient. And that coefficient just explains what's potentially the smallest graph G that is Ramsey for KK. So that's one type of graph to see what's the smallest one possible in some sense. But graphs that are Ramsey for KK can be very different. There are a lot of interesting reasons, because you could think initially that, yeah, just take a graph large enough, and yeah, you will in the end have a monochromatic copy of KK. But there are graphs that are really not necessarily large, not dense, and that are still Ramsey for KK. For example, there is a result from Fockman, I think, and if I'm mistaken, it's in the 70s. I don't know exactly when, but it proved that you can have a graph, Ramsey, let's say for KK. So if you color it with colors, you have a KK inside. But what's impressive is that you don't even have a KK plus 1 in G. So as a subgraph. So yeah, clearly, if you have a large graph like here in K6, yeah, you have a lot of case K3, a lot of K4, a lot of K5 inside. So you end up with a monocomplete K3. But you also have some other graph who are still Ramsey, but they don't even include a click of just size 1 above in the graph. So it's really interesting to usually understand why a graph is a Ramsey. So the Ramsey number is one parameter we want to study quite often. But for today, what we study actually is, in my talk, is the minimum degree. Okay, so we want to understand how small can the minimum degree of graph that is Ramsey for KK can be. Okay, I need a small caveat here, is that imagine that you have a graph here, G, I don't know, do that one here, I might write G, and assume that G is Ramsey for KK. Yeah, so that's fine. But now what I can do is I can add a new vertex V, and I can define G prime to be just G union V. So just is G with just one vertex. There's no additional edges, just this one vertex. And the point is, if I try to color G prime with my colors, because G prime contains G, I will, and because G is Ramsey for KK, I will end up with a monochromatic copy. So I know that G prime is also Ramsey for KK. And the issue now is that the minimum degree of G is 0, because I have this vertex here in G prime, which is degree 0. So you should just ask the silly question, how small can the minimum degree be? Well, it's 0 for any case. So what we want truly now to study is this graph. We want a graph to be Ramsey, not because it contains a subgraph that is Ramsey. We want really like the core reason why a graph is Ramsey. And that's what we call quite often minimal Ramsey. Minimal Ramsey, and we denote them by the set. Okay. So the parameters I'm going to study with you today is these parameters, SR of KK, and we said it's the minimum of the minimum degree over all graphs that are minimal Ramsey for KK. There's a lot of minimal here, but that's what we study. Okay. So if we look at graphs that are Ramsey, the key graphs that are Ramsey for KK, how small can the minimum degree be? And just to give you a bit of history, the parameters was introduced in 1976 in an amazing article by Burr and Lovash, so 3 brilliant people. They introduced that parameters in an article and with different parameters too. And they proved a rather surprising result at the time, that they gave an exact result for 2 colors. So that was surprising, because if you've done any work in Ramsey theory, you know that exact results are quite rare. It's really not common. And it was also really surprising because if you remember Sam's talk, the asymptotic bonds we have for the Ramsey number are exponential. Okay, so in 2 colors, we have these bonds for the Ramsey number, which means that any graph that is Ramsey for KK must contain this number of vertices. Okay, so it's an exponential number of vertices, so it's huge. So when K grows large, the graph, if you want to graph this Ramsey for KK, it's going to be huge. It's going to be more or less exponential in number of vertices. But that result here, what it means that you've got a graph that exists that is Ramsey for KK. So he's going to have a huge number of vertices, but it contains at least one vertex with degree K squared. And that is much, much smaller than exponential. So it's quite small, and you cannot delete that one. If you delete V, you lose Ramsey property. That was a big surprise at the time. And after that article, many people started looking at the parameters, what they can do. For decades, the work was mainly done by switching KK, because the way I've defined it is only for KK, but we can put that graph of Ramsey for another graph. But recently, and especially since that article from Fox, Quishpur, Libanopoulos, and Sabo, people are studying the parameters I want to introduce to you, the multicolor version. So what's happening when you have like more colors? And we know more or less what's happening for asymptotic values. So we know that it's when K is fixed, it's quadratic in the number of colors. And when the size of the peak is fixed, it's quadratic in the size of the peak. And in that article, which is the same as that one, they also provide with this bound, which is a polynomial bound in both terms at the same time for any values, so not asymptotic values. So that result is the one we improved with my co-authors. So John Bamberg, Anwar Bishnoi, and myself. What we did is we proved that actually we improve the exponent for both terms. So if we go to the 5 and we go to the 5 half. Okay. So that's the result I want to explain to you today in the 10 minutes I have, more or less. But as I've said, we use probability, we use group theory, we use finite geometry, we use cubics. So I'm not going to be able to describe everything, but I just want to explain to you the journey more or less, because I think it's quite interesting, at least I think. So the journey starts with something we call color packing, and it's a concept introduced in that article by Fox, Wishbone, Person, and Sabo in 2016. And you don't need to read the definition exactly, but what you need to remember that a color packing is a set of graphs, G1 to GR. They are edge disjoint, that's very important. And actually, I'm going to put that one in green because we're going to follow that condition in different parts of the proof. And they are on the same vertex at N, and they have these two specific properties. But the way you can see that is, we call that a color pattern because you could see that actually just as a way. So let's say that could be my graph G1 in one colors, that my graph G2, and that my graph, I don't know, G3. It doesn't have to be the complete graph in the end. But they're on the same vertex set, and they have two key properties, is that we have a good control of the clicks that are in this graph, okay? So we know that they don't have large click, but if you look at a vertex set large enough, you have a click of size 1 minus. So you don't need to remember exactly that, but you should remember that we have a good control of the size of the click in this graph, okay? And what they prove in this, still the same article, they prove that if you have that kind of color packing on the vertex set of size n, then you have that inequality. So that gives you an upper bound for parameters. And it's a bit strange to see it directly, but the way it's done, just very briefly, it's through something we call gadget graph. And gadget graph are like key graph in this domain. The graph H, we say that H is not Ramsey for our KK, but that means that there exists at least one coloring where you can color without monochromatic KK. But if you try to do that for any such coloring, so for any coloring without monochromatic KK, we have that the two specific H, E, and F have the same colors. So we use this to kind of force some coloring in our graphs, and they use that to prove that. And that's the first probabilistic part, because these graphs are not construction, they are probabilistic construction. So they use, we take a random hypergraph, and from that hypergraph, you can build that kind of graph, gadget graph. So it's the first step where we use probabilities, and that gives us an upper bound for parameters. So now we've got an upper bound, but we need to find this graph, okay? So we need to find graph as disjoint on the same vertex set with some key properties, okay, where we control the clicks. And to do that, we move to finite geometry. And finite geometry is used quite often to build graph when we need some extremal example. Sam did talk about them. And we are going to look at partial linear space, which are just point line incidents, so just points and lines, where between 2 points you have at most one line. And we want them to have a specific order, which means that at every line we contain s+1 point, and at every point you have t+1 lines. So that's, for instance, in the Fano plane of order 2. It's a very classical example. And the way we move from one linear space to one graph is quite usual. Let's say you have one here, partial linear space. We look at something we call the collinearity graph. And it's just a graph, like every point is a vertex, and you join two vertex if they're on the same line. Okay. So here, typically, you have one line, 1, 2, 4, so they form, oh, sorry. That's 4 and that's 3. And there you end up with 1, 2, 4. Okay. But remember that, so that will give us a graph. But one condition we want on our graph at the end in this GI is we want to have a good control on the click inside this graph. So in this kind of graph, the clicks and specifically the triangle, they can come from two sources. The first one is if you have a line, well, obviously you have a triangle in the graph, but also if you have already a triangle in your point line geometry, that gives you a triangle in the graph. So there's one condition we start with, is we're going to look for partial linear space that we call triangle free. Okay. So we know that if we have triangle free partial linear space, we can build this kind of graph, and we have a start of a control on the level of click. And now what we do is we prove something with Anurag and John, which is a derivation of what they did in FGLPS. And what we explain is now if we don't have one, but a family of partial linear space, then each one of these partial linear space, we can use it to control, to build one of these G. So we're gonna have one partial linear space for that one for the second one, and so on. And if they have some nice property, so triangle free is one, what we do actually is instead of building directly this graph, we take a random sorry, not a random permutation, a random partition of each line, and we kind of break them here, more or less, when we build that graph. And we can show that with the probability argument that there's a way to do that, such that we will have all the nice properties we want for, and we will have a nice control of the click. So under the proper condition, we will be able to build from this family of triangle-free partial linear space. We will be able to build our color packing, and the color packing will give us that inequality. It's a long journey. We're getting there one step at a time, and I will give you a summary at the end. Don't worry. So now we've built that. We need to know how do we build it. Okay, so we know that if we got this family of triangle-free partial linear space, we can have our result. So the last step is, as I promised, is group. And sorry, that's should be equal. And for this, we use a construction by Cantor from the 80s. It's quite known. We start from the Eisenberg group on the finite field, a specific one of order K5. So here size here K5. I'm going a bit fast because I don't have too many times. But what Cantor proved in the 80s is there are some subgroups in the Eisenberg group. And if you define your point set to be the group and the lines to be kind of the right cosets, more or less, of these subgroups, it's all you need to remember, then that gives you a partial linear space, triangle free, with a specific order. So that's good. We have one. We know how to build one partial linear space. Now we want to know how do we build a family of partial linear space, because remember that's what we need here. And we need them to be on the same point set. And the advantage of working with a group construction is we can define tau to be an automorphism of E. Okay, and tau is going to act on each subgroup. Okay, so now what we can do when we use Cantor construction is we have the same point set, but instead of looking at the group AI, we can look at the way tau acts on that AI, and each time that's going to give us, for each automorphism, that's going to give us a new partial linear space. Okay, so what we need now, we need actually tau1 and tau R. We need a family of automorphism of E that will give us some new partial space, and we have some condition because we want the line to be disjoint and so on. But so at that point we started saying, okay, we have some ideas, we looked, and the first idea we had, of course, is looking at inner automorphism. But the issue is, remember that condition I talked initially when I wanted like S disjoint? And actually, if you follow that very condition to the very end, you can write it like that. It's the last slide, so it's going to be fine. You can write it like that. What we want a family of automorphism, but we want them to verify a specific condition, mainly that if you take two subgroups of E and you look at the action after two different automorphisms in that family, the intersection should be trivial. And that proves to be difficult. So we couldn't use inner automorphism. We had to look for other automorphism. And we had to look at different ones. We had to read a lot of papers on this topic. And in the end, we found one that could work. And the good thing is, so when we started rewriting that condition using our automorphism, the formula is a bit complex, so I don't need to write it here. We found that that condition was true if and only if we could find a kappa, but in FQ, sorry, such that here we have a cubic. If that cubic was irreducible in FQ squared, we play a bit around it. We use a theorem, recent one from Kim Yi, which proves that that is equivalent to another cubic, irreducible, but now in FQ. And actually, that is something that is known as the Hansen-Mullen conjecture. It was conjectures in the 90s, and it was proven true in 97 and 98. So it might be not very clear now how this conclude the proof, because I will give you the journey and the way back now. But that's actually, from that point, we were done. Because what we've done is we started from the group E, the Heisenberg group key of order Q5, and using Carter construction, that we have now a triangle-free partial linear space of order Q squared Q minus 1. Using the Hansen-Mullen conjectures and irreducible cubic conics, right? We now have a family of this partial linear space with nice conditions, so they don't intersect and so on. Using probability, and we prove that this family of partial linear space, they give us a color packing of graph using the collinear graph. And that one, as a condition, is that that's going to work as long as we have that. So the condition is coming from the order. We need the order of the partial linear space to have some nice property. And as long as we have that, we have a color packing. Then we use probability again to prove that if we have the color packing, it means that our parameters, for which we were interested in, is smaller than the vertex set of the graph, which in our case is the size of E, which is Q5. And so what we do, we want Q to be larger than it is here, and a prime, because it's on the prime vector, sorry, finite field FQ, so prime power, but we're looking at the prime is fine. And yeah, so we just take the smallest prime that is actually larger than that. And by Bertrand postulate, we know that there is a prime below twice that. So here we have an upper bound. We know there is at least one prime that verifies that and that. And so we know that SR is now smaller than Q5, which is just our final result. So it's a lot to take in. I couldn't go into many details, but I really like that proof because I never learned so much stuff that during that work with different people. So it's really something I enjoy doing. And we used a lot of different results. We read a lot of different topics. And in the end, yeah, we have I think a nice result using probabilities, groups, cubics, and so many stuff. So yeah, that's it for me. I beat over time, but just on time.
Thank you, Thomas, for a wonderful talk.
Put back my camera.
Yeah, now we've come to again a time of questions. Are there any questions for Thomas? It is quite a nice result. Just a quick question. I might not have been able to follow. What is the lower C and up capital C?
Yes, just because it's going to be like, so here you have Q that is smaller than twice C, and you need to, sorry, so I'm reversing, it's just power 5. So actually C is going to be, I just take that power 5 because SLKK is smaller than K5, so C is just 2C power 5. In the end, it's going to be something like 25,000. So if we compare to the first initial result by VGLPS, we are improving on the, sorry, where was I here? We are improving on the coefficient here on the exponent, but we lost a bit on the constant. So that C in the end is 25,000, something 25, not K, excuse me.
Right, I see. Okay. So it's an improvement more in the asymptotic case, not so much for small values.
Yes.
Yeah, okay.
But we didn't try to optimize a constant that much. So it's probably doable. And that constant comes really from the fact that when we say that the partial linear space family gives us color packing, we have some specific condition on the order of the partial linear space. And
sorry,
because
say that again.
The lemma where we say that if you have a family of partial linear space, then you have a color packing, so the family of graph. This lemma is true under some condition on the order of the partial linear space. And because the partial linear space have order Q depending on Q, then that gives us a condition on Q.
Right, okay. I see.
It's a lot of details, but the details are not that important. I think it's nice to see that when you talk to the right person, like that article, it took us less than a month to write because I had the probability in my mind. Anurag was finite geometry and he knew the problem. And when he talked with John about that, John was like, "Hey, I know how to build that from a group." And in the end, like in 2 weeks, it was written, and in 1 month, it was sent. So it's good.
Wow, that is very fast. Are there any other questions? I guess I have maybe one final question before we finish up. Yeah, what do you think would be the next directions for trying to improve on the bound? Would it be trying to look at the asymptotic nature and refine it more, or maybe trying to get that constant down?
It's more than asymptotic. There is actually a conjecture that we should be able to go to a squared in both coefficient up to polylog, so k squared and r squared. And it's not obvious, like there's a lot of work that are going around to try to find better finite geometry tools. Like the one we have here, we described from the Heisenberg group is actually a subgeometry of a generalized quadrangle. So it's linked to what Sam talked about when he's talking Ramsey numbers. And yeah, we would love to have like some other construction because as soon as we have other way to build a partial linear space, we can try to apply it in many, many places. But there are a lot of steps here. So each step, like for instance, the probabilistic steps, if we can make them deterministic, there's a chance that we can do something better. And there's a lot of different steps that could be improved. It's not clear yet how to do that. Like which one's going to be the key.
Yeah, okay. All right, well, if there are no other questions, let's thank Thomas again.
Thanks.